Hello everyone, welcome in this webinar organized by the Divico project. Thank you all for attending, and I'm very pleased to be able to make a presentation here about the systemic projects and more specifically on how nutrient recovery and recovery of water and organic matter from digestate from large-scale biogas plants can have an influence. First of all, my name is Marieke Verbeke and I'm working for the Flemish Coordination Centre for Manure Processing. And here you see our website if you would like to have more information. Small words about our organization. We are located in Belgium and in the northern part of Belgium, Flanders, which you can see on the map. We try to coordinate between the Flemish government and the manure processing sector because we have a lot of manure in Flanders. On a small surface, you can imagine that this brings along some problems. We want to be a knowledge center with regard to manure processing and marketing of the end products. And we try to objectively support the Flemish policies around this. We have a unique network of stakeholders in the whole of Europe, and we also hope to increase the supporting base for manure treatment in Flanders. By helping the manure processing sector transition to a more sustainable and circular economy. And that's why we try to disseminate as much as information and communication to our target group of agriculturals and manure processors. We are also involved in European projects, like I mentioned, systemic, for example, because we are looking towards how to be a sustainable sector and circular and advanced circular economy in our sector. So this is a small word about what our organization does. Now, we also organize an international conference on manure management and valorization, which also many times includes anaerobic digestion because it can also be seen as a form of processing manure. Not really processing, but treating manure and trying to recover energy from manure. It's a conference of 2 days and it will be held in the Netherlands in 2022 in May. So feel free to register if you think this might be interesting for you. Now on the systemic project, it's a European funded project that I've been working on the last 4 years. It has very recently ended, and this project is about looking into large-scale anaerobic digestion plants in Europe. They all have in common that they are located in regions where there is an oversupply of feedstocks or manure, for example, and that they are large-scale, meaning like above 20,000 tons per year of feedstocks processing per year, and up to 2 megawatt electricity production capacity, sometimes even more. So we focused on these 5 big plants in different regions, and for these plants we were doing the whole schemes of nutrient recovery that they have installed. So these 5 plants have installed nutrient recovery technologies for digestate. We have been doing mass balances, energy balances for those 5 plants. Also doing LCAs, so life cycle assessments. We have been trying to figure out how their business case is working, and also try to see what are the policy barriers, legislative experts in the region, but also in the whole of Europe. And my work package was focusing on transferring the technologies that they have implemented to more biogas plants in Europe. And how do we do that effectively? So we have gathered 10 extra biogas plants that were very interested in the technologies to recover nutrients and water from digestate. And these would be our outreach locations to which we would like to transfer our experience and knowledge. And then there were even more biogas plants that were also interested. So these were like our first followers. The idea was that the systemic consortium of partners would function as an initiator, a stakeholder, but also intermediate or facilitator of supporting this learning experience and exchange about nutrient recovery from digestates. How did we do that? We set up living lab meetings, which were meetings with all the biogas plant owners discussing these technologies, their experiences with it, trying to get them over to each other to see really the technologies, and then having a digital part where they could find also all information. So that about systemic for now. What I learned from the situation in Argentina from the DBGO project is that there were about 100 biogas plants in 2015. Most of them were there because of environmental aspects, and only a small part was there because of the energy production they could get from anaerobic digestion. Most of them are small scaled, and they mainly process industrial waste, organic waste, or biomass. But in the last few years, apparently, there was an important development in technology providers from Europe, and there were new renewable energy targets set, so the biogas sector was more stimulated. And they have seen new biogas projects coming up in Argentina, large biogas projects like with from 1 to 7 megawatts production capacity. And there is also a potential for the feedstocks, like there is enough pig manure, there is enough dairy waste or food industry waste that could that could be processed in these anaerobic digestion plants and valorized in the form of energy. However, the current technologies for digestate treatment are just complete mixing or just store it in covered lagoon and apply it on land. Now, what are the problems or the conditions in Argentina? There is enough land, so we cannot really compare it to Europe, where we have very lower surface to spread all the digestates. In Argentina, there's no problem. There is enough land and there are no restrictions on nutrient surpluses in the soils, which is of course a good thing. However, there is a question about how to apply digestates. Application methods cannot compact the soil, or there should be no tillage. It would also be beneficial if there could be a reduction of emissions of NOx and ammonia while applying the digestate as a fertilizer. And also reducing transport cost is an important factor, because when you're working with digestate, this is like a liquid product. You don't want to transport it too far, because transporting water is just a waste of money. And also there could be in the near future or in the further future a potential market which could bring revenues, a potential market for like specific organic fertilizers made from digestate or for digestate as such. So this needs to be further developed first. Then there is a question about using separated digestate as bedding material for cows, and if the heat from the CHP could be optimally valorized. So these are all things we need to take into account when looking to the biogas sector in Argentina and trying to implement technologies for digestate processing. I will now try to give you some examples we have from the systemic project, which is on European scale and on European level. Maybe not everything is comparable to Argentina. However, the idea is just to give you some inspiration on what is possible. So in Europe, we and in systemic projects specifically, we have studied large-scale anaerobic digestion plants. Most of them were from 1 to 2 megawatts electricity capacity, production capacity, and there are even some higher that could produce up to 7 megawatts electricity. This translates roughly to 20,000 to 300,000 tons of feedstock going into the anaerobic digester per year. So then you have more or less an idea of what I mean with large-scale anaerobic digestion plants. Now, first of all, the first step to recover energy or nutrients, organic matter, and water from digestate, first step is separation. Because then you separate the water fraction from the solid, the dry mass. And an advantage is you can also separate phosphorus. If you efficiently can separate dry matter like fibers, you can use this as a bedding material. At least in Europe, it can be used under the condition that it is pasteurized, which means that it stays 1 hour at 70 degrees. So these are some indicative values of what different separation technologies can do for digestates. First thing you see here is the centrifuge, decanter centrifuge, which is mainly used for digestates in Europe. And these values are separation efficiency going to the solid fraction. This means, for example, 12% of the mass of the initial digestate is going to solid fraction. And here you have dry matter, organic matter, total nitrogen, ammonia nitrogen, phosphorus, and potassium. The other column is the efficiency you get when you add coagulants or flocculants, which are additives that could help or support your separation. In Flanders or in Europe, in certain regions, it's important that you try to recover the phosphorus in the solid fraction, and therefore you see here that you would like to have as much phosphorus in the solid fraction as possible. Therefore, applying coagulants or flocculants can really help you with that. The second one is a screw press, which is more used on, for example, more fibrous digestates or cattle manure, for example, because it works better when there's more dry matter. This is mainly used, for example, making bedding material for cows. Then you have a belt separator, which are belts moving along a row of lines, and they are pressing the liquid out. This is also always used with coagulants. And then there is a DAF, a dissolved air flotation unit, which is more like the second step of separation. It's to get out more of the solids if you want to go further in purifying your digestate. So it's not like it's the first step. You can have, for example, a centrifuge and a DAF, and then a further treatment cascade. These things here on the right are some specialties. This is separation in the stables already of manure. So it's even before anaerobic digestion. It's to separate the urine from the feces of the animals so that it's already at source separation. This can help with improved anaerobic digestion, for example, because then you only put the solid fraction in your digester, which gives you better biogas yield, for example. But these are very specific stable systems, of course. Now, a small overview of what I just mentioned in my slide about which things should be taken into account for the products that are coming out of the separation technologies. We call it solid fraction and liquid fraction. Okay, if you would see the separation technology, is it complex? No, it's relatively easy also to operate, to maintain. It's just a screw or a decanter centrifuge is just a tumbling chamber. So it's relatively low in complexity. You can use additives, like I mentioned, for improved phosphorus separation, for example, but it also counts for an extra cost, obviously. And you add chemicals to your digestate, which is also not always wanted. Can you reuse heat from the CHP? No, not for the system itself, because it doesn't require heat. It can when you want to dry your solid fraction after, which is advised because then you lower the volume or the mass even more of your solid fraction, and then you get a dry product up to even 90% dry matter, which is like really, really dry, and it can be spreaded very easily. So drying is can be interesting, and you can reuse the heat. How do you use these products, solid fraction and liquid fraction? The solid fraction can be used as a soil improver, for example, or fertilizer, because it still contains a lot of organic matter. Almost all the organic matter goes to the solid fraction. All the phosphorus is also linked to the organic matter. Let's say the main part of the phosphorus, and organic nitrogen also stays in the solid fraction. Like I said, solid fraction can be used as bedding material, but after pasteurization, then it's rather safe to be used as bedding material for cows. Then the liquid fraction, it is a liquid fertilizer. It contains still a lot of nutrients and organic matter, soluble phosphorus, mainly the ammonia, nitrogen, and potassium and other dissolved elements. So it's a good fertilizer, and yeah, it has an effect on, for example, here the transport. The solid fraction, you can obviously go further with it because it has a lower mass. It's also drier, so you can drive it away further at lower costs. Liquid fraction would be advised to apply it more locally because transporting water is just an extra cost. Application. When it's a dry product, you can just spread it widely with a normal spreader. For liquid fraction, it's advised to do soil injection because then you really reduce ammonia emissions, the possible ammonia emissions coming from the liquid fraction. Is there a potential for specialized fertilizers from these products compared to raw digestate? Yes, because here you have more or less concentrated nutrients in the solid fraction, meaning phosphorus is concentrated, organic nitrogen is concentrated, and organic matter. So this is a very nice product compared to digestate because it doesn't have that volatile ammonia, or not much, and the liquid fraction is the opposite. It has this ready available nitrogen in a liquid. So depending on the crops you're cultivating, one or the two products could be even more interesting than raw digestate. Something about application technologies. This is a picture of widespreading of dried solid fraction. For example, injection technologies. These are like different types of machines that are used in Europe to inject liquids into the soil for crop cultivation and to reduce NOx and ammonia emissions to the air. Then the next technology I would like to talk about is membrane filtration and reverse osmosis. It's relatively new on digestate and manure, but for example in the Netherlands they have now been focusing a lot on this technology because they think it's most promising for the future. What does it do? You have a digester here. This is the example of biogás plant in the Netherlands. They separate the digestate with a centrifuge. Afterwards, they have membrane filtration units, microfiltration, and reverse osmosis. And then they have an ion exchanger to really purify the water into a clean water that can be discharged. What is coming out is a concentrate. They call it concentrate, but it's actually not really concentrated. It's a liquid with mainly all the nutrients in it. Here you see a scheme of what the membranes do. So they just keep all the micromolecules and salts, retain them, and only the purified water goes out. These are some suppliers, but of course there are many more. And this is a rough estimation of the composition of the mineral concentrates. That's how they call it, but let's call it the RO, the reverse osmosis concentrate. You can see that the pH is rather high, up to 8. And I call it concentrate, but it's not really concentrated because, for example, the nitrogen content is only 8 grams per kilogram, for example. So it's like a very diluted nutrient solution, let's say. Pros and cons of the different products. The technology complexity. I'm talking now about the whole cascades, microfiltration, reverse osmosis, and ion exchange after each other. It's quite complex to operate, and it's also really sensitive, especially the reverse osmosis unit. You cannot go to it with a high dry matter content, otherwise it just clogs, and then you have to replace the membranes, which is an additional cost. So you have to have staff that's really experienced, that needs to get the feeling how these technologies are working and what can disturb them. You have to have like a stable process also in your digester, because fluctuations can really foul the membranes, for example. And therefore an advanced pre-treatment is needed. And I'm thinking here about a very good first step. Like I mentioned, the separation should be very robust. You would have a constant end product. So the liquid fraction after separation, which is going into your membranes, should be rather constant of composition to have no problems in later steps. So this has an impact on maintenance and operational costs, as you can imagine. Also, it requires some additives. You need acid for conditioning the reverse osmosis membranes. You need cleaning chemicals, acid base, to clean the membranes every month, every 2 weeks. So be aware that you need chemicals. Can you reuse the heat from the CHP? No, not really. Heat is not required for membrane filtration. However, you can use part of your green electricity, of course, to run the system. Make sure that you are also producing some other byproducts which you need to get rid of or make use of, let's say. For example, the solid fraction, when you separate the digestate first, which is normally what you should do when you are implementing this cascade. If you have a DAF as a second cleaning for removal of solids, dissolved air flotation unit, you will have some sludge coming out of that. You also will probably need to do something with. You can recirculate it back to the digester, or you can mix it with your solid fraction, but you still need to do something with it. And then there's a certain amount of solids coming from your microfiltration too. So be aware of that these are not the only two products that are coming out of this cascade. On the other hand, what can you do with this product? The reverse osmosis concentrate can be used as a liquid fertilizer because, like I said, it contains all the nutrients and water. And then the purified water, it is dischargeable, or you can use it as irrigation water. And as you can imagine, the raw concentrate has a much lower volume than the initial digestate, so you win in volume. It's maximally reduced and it's concentrated in a much smaller form. However, it's still a liquid. So transport, because it's a liquid, try to use it locally or as fertigation as possible. And the purified water, you can discharge it or also use it as irrigation water. This will, like I said, give you reduced transport costs compared to if you would have raw digestates. How to apply this? The reverse osmosis concentrate needs to be applied with soil injection because it's, like I said, it has a higher pH which can volatilize the ammonia again, and then you have ammonia emissions. So reduce that, don't go widespreading everything or all the ammonia is just lost in the air. You get burning of the plants, etc. Is there potential for specialized fertilizers? Yes, this is very much a different product than raw digestate. It's more clear liquid. It has all nutrients concentrated in a smaller volume. So it is definitely a different product than digestate, which could be tailored to the needs of specific crops, for example. Then there's ammonia stripping scrubbing technology, which might not be interesting for Argentina, but I can still mention it. It's a technology to get a nitrogen out of the digestates or out of nitrogen-rich gas, like stable air, for example. the way what you do is you try to get ammonia in liquid or in gas to ammonia gas form, and this ammonia gas you then try to scrub away with acids and capture it in the liquid. The end product is an ammonium salt solution, and then you have a clean stream of air or liquid, relatively free from nitrogen, ammonia. These are different configurations that you can have. You can have side stream from air. So if you have a nitrogen-rich loaded air, you can reduce ammonia emissions to the air by first scrubbing the ammonia out of the air. You can also put a scrubber, scrubbing installation inline with your digester. This is mainly done if there are, for example, high amounts of ammonia in the digester because of the use of, for example, poultry manure. This brings toxicity in the digester and reduces the biogas yields. Therefore, if you strip and then recirculate the stripped digestate, you can have a higher biogas potential. And then there is also just side stream stripping, which means you take your digestate and you strip the ammonia from the digestate, and then you have a digestate low in ammonia and a scrubber salt solution. So that's just a way to recover the ammonia in a different kind of solution. I'll go a bit deeper into this. For example, here, this case here in Italy has an inline stripping scrubbing because they are using sewage sludge with high ammonia levels. It brought toxicity in their digester. They have a stripper here and they recirculate the stripped digestate back, and then they have higher biogas yields. These are two installations. One is here on the liquid fraction of raw pig manure, and they scrub the ammonia with nitric acid, which then produces an ammonia nitrate solution, and stripped pig manure. Same as tried for cattle manure. It was more difficult because there were more pre-treatment steps necessary. And then there is something that's done very frequently in Europe, which is air washing, meaning from the air from the stables of the cows or the pigs is washed with more or less the same system so that there is no ammonia emission from the stables to the outside air. So there the air is scrubbed into a with sulfuric acid to ammonium sulfate solution. Here are some indicative values of how these scrubber salt solutions look. If you have scrubber salt from an air washing system, these are the compositions. You can see that the pH is rather low and that the nitrogen is about 3 to 8% of the solution. If you have ammonium sulfate from raw digestates, so more or less the same concentration. However, the pH can be a bit higher. Ammonia nitrate also the same, but you have higher nitrogen levels because you, of course, have ammonia nitrate. So you have twice the nitrate here. You have also sulfur. The other product you get is nitrogen stripped digestate. So digestate with a low amount of nitrogen in it. All right, these are again the advantages and the disadvantages. The technology is quite complex. You need acids for scrubbing the nitrogen out. Can you reduce the heat? Yes, because you need heating to get your nitrogen into the gas phase, and preferably you need to strip CO2 first to increase the pH to optimize this transfer of nitrogen from liquids to gas. How can you use the scrubber salt solution as a liquid fertilizer? It has the advantage of being like a single nutrient fertilizer. It only contains water, nitrogen, and then sulfur, for example. The stripped digestate is then the same as the normal digestate, however, it has a reduced nitrogen content, which could be interesting in some cases. How do you use it? Preferably local because they are both liquid products and there is no real volume reduction of the digestate, so this might be not the interesting thing for Argentina. However, if you want to apply it, the nitrogen scrubber salt solution, please do it with soil injection or adapted machinery under specific conditions do really prevent ammonia volatilization and leaf burning. Strip digestate, yeah, you can apply it with soil injection also. In theory, it's not necessary because you have stripped the digestate of nitrogen, so emissions would be very much reduced. Is there potential for specialized products? Yes, this scrubber salt solution is, like I said, a single nutrient fertilizer, and it could be a replacement for synthetic nitrogen fertilizers. The strip digestate, I'm not sure if this is an interesting product in Argentina because there's no nitrogen surplus in the soil. These are some different technologies or machineries to apply the scrubber salt solutions. I'm not going to read this because I'm not really an expert on application machinery, but these are some things they used in Europe. Spoke wheel injection, row injector, and here you have like trail hoses, drag hoses, which is no injection. These are conditions you have to watch out with when you are spraying the ammonia scrubber salt solution. Because if you use it as a leaf fertilizer, you have to really watch out what you're doing because of the acid pH and the possibility of the volatilization of ammonia. You can have leaf burning, except under certain conditions when you can use it. There's a special system in Germany that does ammonia stripping without any use of acids. They use recovered gypsum, and this is their cascade. However, there's only one plant really operational now. The special thing here is that they also produce from the stripped digestate, they separate fibers and they make cardboard, paper from it. But therefore you need to have a very specific feedstock, like with a lot of fibers, like with grass or and chicken manure. Then the final thing I want to talk about is evaporation technology. It's also a way to reduce the volume of the digestates, and there are two ways you can do this. First of all, you have an evaporator, and if you just put in there liquid fraction of digestates, it evaporates water, but ammonia also volatilizes, so you get an ammonia water solution when it condenses, and a concentrate of all the other nutrients and organic matter. So like you see here, you get ammonia water of 10 to 20% of nitrogen ammonia. You can, and then you have processed water, which you can purify further and hopefully discharges. So you have the reduction of volume there. Another way you want to keep the ammonia in your concentrate is just add some acid, and then everything is in the concentrated digestate. And what comes out is a very low nitrogen condensate, which you can further purify and discharge. So this is a way to really reduce the volume by extracting water from your digestates. There are different configurations for evaporators, so be aware that it's very complex technology and you need an advanced pre-treatment because the higher dry matter you send or the higher organic matter you send into your evaporator, the less efficient it will work. You also need additives for acidification of your digestate if you want to prevent nitrogen from going into your condensate, or for your conditioning of the reverse osmosis. You can obviously use the heat from your CHP because you will need to heat up the evaporator. Make sure you are also producing other projects than just concentrate and purified water. You are also making, in the first case, ammonia water, which is not a nice product you want to have, which is just ammonia solved in water. and it has very high pH, so you cannot do anything with it except trying to convert it to ammonia sulfate maybe. It can be used as an NOx reagent in incineration ovens, for example. So if there's an incineration plant nearby, you can use this as an alternative for ammonia solution or urea solution, for example. However, it's a high-risk product, so be aware. And you will also have some processed water, which still contains low nitrogen concentrations. So it's not just able to be discharged. This makes maybe in total this process not always interesting, but you need to see for your case, for your biogas plants, if it's interesting or not. How can the products be used? The evaporator concentrates is like 20 to 30% of dry matter. It contains all nutrients, all salts, which means it's like a very concentrated, salty product, not comparable to digestate. What can you do with it? You can mix it with your solid fraction and dry it. And then you have like a specialized fertilizer, with which you can play with the nutrient content by mixing different amounts. And the purified water, of course, you can discharge it or use irrigation water. Transport, if it's a dry product, you can go transport it further because you have lower mass. The purified water, as I said, can be discharged, and the evaporator concentrate, don't use it as such as a fertilizers because it's too salty, too concentrated. Like I said here before, mix it with other fertilizers, with solid fraction of manure, with solid fraction of digestate, so you can have more or less a tailor-made product. Preferably dry it, pelletize it, then you have like this specific fertilizer. Now, small thing about the revenue potential of these new products as specialized fertilizers. These are all relatively new products, unknown products. Even digestate as such is a new product for a lot of farmers. So, but we see that there could be an interesting untapped revenue potential for all these products. What can you do? First of all, the low-hanging fruits are making blends of the different nutrient compositions. So taking ammonia sulfate, try to mix it with solid fraction so you can really tailor the NPK value of your fertilizer towards the needs of certain crops. The second option is going into niche markets, which I will give a bit more information on later. Currently, apparently in Argentina, there's no culture yet of using digestate or digestate-derived product as a fertilizer, which could be a bottleneck. That is because the farmers are not familiar with specific application methods and they don't know the product yet. They don't trust it yet, maybe. So what do you need to do first? First, try to optimize your product towards the needs of a defined consumer group. For example, if you say, okay, I want to make this tailor-made organic fertilizer from digestate, so I can get higher revenues from it, you have to make sure that it's the right form, maybe a pellet, or that it doesn't smell, that it has the right nutrient content for specific crops in the area, that it can be applied user-friendly, so you have to make contacts with people having the right machinery. Maybe you have to design some machinery yourself. And very important, don't forget, you need a dedicated market strategy to reach higher revenues. Try to give demonstrations, express the green image of your products, etc. So it's not that easy. Something from the Dibico project, from their survey. What are biogas plants in Argentina looking for when they are looking for training opportunities? And here a lot of them said, although it's more or less 50-50, we want to know how to start up, maintenance, operation system, proper technology selection. So this is what I remembered from this survey. And in the systemic projects, we have been trying to transfer our experiences and studies to the target group of biogas plant owners in Europe. How did we do that? We were trying to, instead of making long reports with information, trying to convert this to an easy readable information package, the business development package, which is a site on our systemic project webpage. It's divided in 6 domains, and here are the most interesting things maybe for your country. In the first thing, we talk about technologies and mass balances. We have developed a tool that makes a simulation of mass balances of the different technologies I have just described. And there's a very interesting webinar online about advanced separation of digestate. So the first step there, this thing is about business case and economical values, legislation more dedicated to Europe, so probably not so interesting for Argentina. And then we have product fact sheets, which could be interesting. So all the products I've mentioned before, there's a lot of details there in product fact sheets. Then how to develop niche markets. So that's already advanced when you have chosen which products you would like to make or create. And I think the most important thing is a contact page, not only to the systemic consortium of academics, but also to the biogas plants who are involved there. This is a short thing about the tool we have developed. Like I said, it's a tool that you can simulate with your own digestate composition which product would come out. So it's mass balances, and it's also giving you the opportunity to estimate very roughly the costs, so the investment costs and the operational costs. And there are a lot of information sheets available too. It will be available from January next year. And there's also be a Spanish version, which could be useful. So this was my presentation. If you would like to have much more information, please have a look at systemicproject.eu. Here under BDP, you can have all the information I have mentioned in my previous slides. And if you would like to contact someone from our project consortium, this is the email address. I would like to thank you all very much for your attention. And yeah, I hope we can evolve the biogas sector into a sustainable sector with circular use of nutrients and organic matter and water. Thank you.